The pressure is on at China's Bird's Nest Stadium. Following a delay of 6 months, the engineers are now chasing the Olympic deadline. Workforce numbers soon swell to 7,000, and with foundations in place, the next key stage is to build the concrete stadium bowl. There will be more than 90,000 seats, and each will need a clear view of the sporting action.
I'm a great believer in getting a great atmosphere in the stadium, and one of the most important factors is to bring people close to the action. Now, the only way we can really do this is to make stadiums steeper and steeper, but of course there are considerations of safety and comfort.
It's a balancing act. As you make a stadium steeper, it reaches a point where it's uncomfortable for the spectators. But make it too shallow, and the seats are pushed further away from the action, leaving people at the back with a poor view. Parrish spends weeks drawing up his plans. To ensure clear lines of sight, he's had to make the top sections as steep as 35 degrees. When the Chinese clients see the plans, they're concerned that 35 degrees is too steep for comfort. They request changes, with seating not to exceed 30 degrees.
On the right-hand screen, we've got the stadium bowl as it is now, and this is based on a maximum angle of 35 degrees. Now I'm going to add another section, and this is based on the new criteria. So the consequence is that while we provide a good view, a better view, we're moving everybody further away from the action. Here on the right, the new one. Now what does this really mean for the stadium? Here is the original one, and here is what it becomes when we put the new values in. The building has got bigger, a huge 22% increase in the footprint. Now, this very quickly equates to many tens of millions of dollars of additional cost. Now, we showed this to the client, and it took them about 2 minutes to say, let's stick with the original design.
With everybody now in agreement, Arab set to work planning the build process for the concrete bowl. First, they must build an intricate concrete frame in 3 tiers. It's like a skeleton that will hold the carefully cast seating sections. Then, slotting into this frame, the 14,700 prefabricated concrete slabs that will make up the seating stands. The reinforced slabs arrive on site. Each is individually molded and can weigh as much as 18 tons. The thousands of slabs are cast in subtly different shapes, and if they're more than 2 millimeters out, the engineers will run into a major problem.
All the plates have fixed connections in between and cannot be adjusted. This means if one plate is not installed in the right place, it will be impossible to install the entire row.
This would be unthinkable. The entire project would be held up while a flawed block was recast. They've got to get it right first time, every time. It takes 12 months to make and position all 14,700 slabs. But finally, the last piece of this giant concrete jigsaw is slotted into place. By November 2005, the stadium bowl has taken form. Soon it will be hidden by the steel exoskeleton, but Li Julin will always be proud of his firm's work.
The exterior steel structure is a very important element in the architectural design. It is beautiful, but the concrete structure inside is just as important. It not only accommodates 91,000 audience members, but also carries out most of the functions of the building.
The most challenging phase of all is now poised to begin. The construction of the steel skeleton of the bird's nest. It's this unique steel structure that will make the bird's nest iconic. The design calls for a series of interwoven steel trusses, up to 313 meters long, surrounding the inner concrete bowl. It's a complex web of steel elements that support each other, just like the interwoven twigs of a real bird's nest.
Structural engineers in China have dealt with many kinds of steel designs, but we have never come across a building of this shape and of this type of structure. This is a difficult job.
In total, there will be an astonishing 36 kilometers of steel wrapping around the stadium.
The prior concern was that there had to be a technological breakthrough. The structure has a double twist, and you could tell by looking at it that it wouldn't be easy to make.
In a conventional symmetrical building, all the forces travel to the ground vertically. Not so in the bird's nest. The structure is made up of thousands of individual beams, all exerting force in different directions. Somehow, engineers need to predict exactly how much force will flow through every single one of these beams.
The real challenge for the engineering team is then dealing with those forces safely and efficiently and making the best use of the materials available in order to take the loads down to the foundations.
But calculating stresses and loads in curved beams is tricky. And there's an added problem. Beijing lies in the heart of a major seismic activity zone. One of the world's worst earthquakes hit China in 1976. The stadium must be able to withstand an earthquake.
It was imperative that we optimize the structure as much as possible to keep the weight down, to reduce the forces from the earthquake.
The only way to reduce the internal forces is by making the beams as lightweight as possible, but without compromising their strength. It's a complex equation, with individual beams needing to be of different thicknesses. Conventional information technology is not up to the job of juggling such intricate forces and shapes.
We actually looked at what is used in the aerospace industry, which is a piece of software called CATIA.
CATIA software is a three-dimensional modeling program that was initially developed for use in aviation. It's capable of designing complicated shapes and solving engineering equations in record time. Simpson puts it to work planning the complex forms and layout of steel structure and beams.
Now this is the main load-bearing frame of the stadium, and then on top of that we then wrapped other elements such as the secondary structure and the stir structure, which gave this appearance of randomness.
The symmetrical and more conventional beam structure is now hidden behind the interwoven random-looking beams.
This successive layering of logical geometry actually gives this illusion of this random geometry, which helps give it this organic shape and helped with the naming of it as the bird's nest.
Thanks to aerospace software, the engineers are triumphant. They have a precise plan for how to make and erect the intricate steel structure. The job of actually manufacturing these steel jigsaw pieces falls to steel expert Wang Lin.
Building a steel structure with straight edges isn't a problem for us. But the structure for the bird's nest looks like a fried dough twist, and it presented us with a big problem.
While the beam sections are assembled in the factory, engineers start work on the base of the steel structure. They begin with the 24 mighty steel anchor points, or feet, that sit at the base of each column. Workers carefully inch them into position. It takes several months to install them all. Weighing 100 tons apiece, these elements form a critical part of the structure. The columns will then be built above them and will channel down much of the weight of the structure into the foundations. The support columns are far more massive than in most conventional stadia.
Each column weighs over 1,000 tons, and there's no hoisting equipment that's large enough to lift it up.
Even the biggest crawler crane in China would be unable to lift an entire 1,000-ton column. The only way to erect them is to break them down.
Each column was divided into several parts for manufacture in the factory and then assembled on site.
These enormous subsections are then raised onto a giant jig where they're built up into column portions. There's still mighty loads to lift. And if anything was to go wrong, the consequences could be disastrous.